Thank you, everybody, for joining us this morning. I am Kathleen Howell. I'm an Associate Dean in Engineering. And I'm really delighted this morning to introduce Dan Elliott on behalf of Dean Jameson and the Office of Academic Affairs. But let me start a little bit by talking about how this series came about and what it is. This celebration of faculty careers actually came out of the last College of Engineering strategic plan. And one of the actions from that plan was called the Faculty of 2020. And it was focusing on professional development at all stages of faculty careers. So, and in particular, aligning the criteria for promotion along with the hiring process and the evolving scope of the college as we started to expand and so on. At that time, there was a desire for a post-promotion review, particularly for full professors, that would feature the accomplishments of the individual as well as provide an opportunity for them to plan perhaps what was going forward, or at least to interact directly with the dean on their particular program and their accomplishments in terms of the college. So full professors who are at least 7 years past promotion are now participating in this event. They get to highlight their achievements to their peers. And although it's also followed by a session with the dean, there has been some unexpected benefits associated with this program. And one of those is the opportunity to share with our peers exactly what different members of your individual units are accomplishing. And so that's been a big plus. The first pilot of this program was in 2013, and we're now into the implementation phase, and Dan is the latest recipient, right? I would also like to say a few words about him then. Actually, I've known Dan for a long time.
Yeah.
Okay, and I'm really happy to see him go forth and do this. He actually completed his PhD in 1981 at the University of Michigan. Before he joined the faculty here at Purdue, he had a postdoc at the Joint Institute for Laboratory Astrophysics and at the University of Munich. He's been here at Purdue since 1984. He currently has a joint appointment as a professor of electrical and computer engineering and a professor of physics and astronomy. He has served ECE, I think, fantastically throughout the years, including as graduate coordinator, the director of graduate recruiting and retention, also for the College of Engineering. I really want to say congratulations to Dan.
Thank you.
And I'm looking forward to hearing more about, I guess, your look back and look ahead.
That's right. Thank you. We keep this interactive, right? So I get bored if I sit for an hour in an audience, so please ask questions and interrupt, and maybe you'll give me some new research ideas too as we go on. Actually, my title is wrong. Our first paper was actually published in 1990, so it's been 26 years now. So you learn something as you look back and you forget these dates, and well, how could it have been so long? So we have been working in a field that we were actually able to first develop. It's an idea of causing intentionally interferences between different transitions in atomic systems, but it's been extended to other systems as well in order to affect the outcome. And we've moved on more recently as a means of using it for detection of very, very, very weak signals in atomic systems that can be useful as well. I wanted to list some of the other things that we worked in here as well. So the coherent interfering interactions will be the topic of today's talk. But other things we've done some work in over the years have been ultra-cold molecules. That's been a collaborative program with Yong Chen, where we are creating and cooling and manipulating lithium rubidium molecules for various purposes. Some early work, which Gerhard I saw, we worked on together a long time ago, was to artificially create fluctuations, impose fluctuations onto a laser in order to create bandwidth and to understand how those correlations affected various nonlinear interactions. We've done a lot of work in using angular distributions from photoelectrons in atomic systems again, in order to probe various things. And some of the best work, I think, but never got any future you look back on these things and you check the citations and it never went anywhere, but it's some of the best work I think that came out of our laboratory. We were able to do four-wave mixing in atomic systems, a two-level system, really well-controlled system, and actually show that some of the fundamental theory that developed for that process was right. But it was, 10 years after people had gone on to the application stage and never took off. Anyways, that's one thing that you learn as you look back on some things that you've done over the years. Of course, none of this work goes anywhere without good students working on it. And so just the students who have been working on the work that I'll be talking about today are listed here, starting with Chen Se and Yin Yin back in the early 90s, all the way up through some current students who are continuing with this work. Okay, now the idea for what I'll be talking about today is that optical interactions in atomic systems can be made to interfere. The idea for this first came to me from some work that had been done in the late 70s and early 80s. Most of you probably don't remember those years. But they were good years too. It was the case of the disappearing resonances. And it sounds like a super sleuth story. People were looking at all sorts of nonlinear interactions in atomic gases. And noticed that at frequencies where they expected to see strong ionization signals, things disappeared. And so here I took an excerpt from a paper by John Miller and Bob Compton. In this work, they were working in atomic xenon. They tuned their laser to a 2-photon resonance, and they looked at the ionization signal. And here they've plotted the various ionization signals as they're increasing the density of the gas. And you notice that the signal tends to disappear, and at higher densities it went away even further. They also monitored the amount of third harmonic generated in that gas. Third harmonic is a coherent process. It's a nonlinear process that can occur in these gases, and it simply means that you're generating light at 3 times the frequency of the input light. And they obviously, it's as you increase the density, you have more atoms to interact with, and so the signal goes up and up and up. So the correlation eventually was noted that as the third harmonic signal went up, the ionization signal went away. In many of these cases, this is not the only example of it, but there were quite a few cases like this. And the explanation being that as the third harmonic is generated, now you have 2 processes going on inside this gas at the same time. There's an interference which can take place between the transition from the initial state to the final state. And that was shown by Jim Wynn about that same time, that these 2 interfering interactions would gravitate towards a destructive interference case, and the signal would go away. Well, when we saw some of those papers, I thought, well, wouldn't it be great if we could separate them? This was all going on inside of a single gas cell, complicated situation. I wanted to pull those 2 processes apart. And that was the beginning of the idea then for these coherent interfering interactions. So we chose mercury, which was one of the systems in which a lot of this work took place. There's a strong transition in the visible. It's a 3-photon transition, so you can simultaneously absorb 3 photons from the laser field. And the idea for the interference now should be that the total transition rate, which I represent by W here, depends not just on the amplitude for the process, but on the sum of the amplitudes, and it's that quantity which is squared. I have to understand something about the amplitude for the processes. For a 1-photon process, it's just proportional to the electric field. Usually we don't bother to write down the phase of the electric field because it's not usually relevant. 3-photon process, well, you're absorbing 3 photons from the field at the same time. It goes as the cube of that laser field. And again, we don't usually bother to write down the phase, but I'll do it here because it does become important here. I'm going to add these 2 amplitudes in order to understand the total net transition rate. And now the phase becomes important because I can change the phase between those 2 processes. I'm going to back up a little bit and tell you something you all know, and that is just interference in optics. Here's a classic experiment of Young's double slit experiment. This is in all the introductory physics texts. You have a source, you have a screen with a couple slits in it. You put a screen over here where you observe the intensity of the light. Works better if you use a laser, but it can work with a light bulb too if the conditions are right. What you see on this screen then would be a series of dark and bright fringes, because the light from the source to the screen can take two paths, and whether we get a bright fringe or a dark fringe depends upon whether those two paths add in phase with each other or out of phase with each other. If they add in phase, we get constructive interference and we get bright fringe. If they add out of phase, we get destructive interference and it's dark. A well-known process since the day of Newton. Young, not Newton. I've lost my history now. When was Young around? Was it before Newton?
About 1800.
Yeah. Okay, younger. I have trouble with fall forward and leap backwards too. Okay, so this is I'm giving you as an analogy because it's a well-known process in optics. But I want to stress the interference that we observe and that we exploit is not an optical interference. We are looking at interference between atomic transitions, not light. And here was the first demonstration then. This was work done by Chen Se. We took a laser which was tuned to the three-photon resonance in mercury. We focused it into the first cell. This is where we generate harmonic light. And so we create the third harmonic of that fundamental frequency. So coming out of the first cell, we have two separate frequencies. We collected the light on a spherical mirror. We focused that light with a second spherical mirror into another cell, and that's where we generate now an ionization signal on the resonance in mercury between the 6s state and the 6p state. And as we change the phase between the omega and the 3 omega light, we're able to modulate now the net ionization rate within that cell. How do you change the phase? In this case, we had this cell in the center, which I'm calling the delay cell, and we simply introduce some argon gas. As we change the density of the gas, it has a different refractive index in the visible and the UV, and so we can change the phase between those two laser fields and modulate the signal. If you look at the numbers on the ionization signal there, that's not real deep modulation, and there are a couple things going on. One is that as a focused beam goes through its focal region, there's actually a phase shift of that beam, as it's just a diffraction effect. I didn't learn until many, many years later that it's called the Gouy phase, which I'm probably not even saying right. But if you've done any work with focused Gaussian beams, you'll recognize this inverse tangent of z over z naught term, where z naught is just the length of the interaction region. Okay, well, we have two beams going through the cell. They're both focused roughly the same, but one of the three-photon interaction depends upon the cube of that laser field, and so it goes through a 3 pi phase shift as you go through the focal region. So we set up a same cell, but with a different electrode configuration in there. It's now a series of 8 different electrodes, and resolution isn't real great here, but this is picking up the signal. So as you look at the 8 different channels across there, each channel is sensitive to the electrons generated closest to it. And so we're seeing a variation in the phase of the two beams there. You see sinusoidal modulation in each one of those signals, but if you look carefully, you can see that the different signals, the different channels are shifting a little bit to the left as we go from one signal to the next. And we can plot that out. We can do it for different tightness of focusing across there, and we can see the modulation shifting due to this phase variation of the focused Gaussian beam. I had a friend from graduate school who we kept in touch as we were going various locations. As I followed him for a while, but never overlapped again. Arlie Smith, who said to me one day, you know, you're doing lots of work with photoelectron angular distributions, and you're doing lots of work with coherent interferences. Why don't you put the two together and see if you can't use the interference as a way of controlling the angular distribution of the electrons which are generated. So these are some simulations we did. This is not a measurement yet. But we just considered something like ionization, photoionization of atomic rubidium. Rubidium has a nice hydrogen-like character to it in that it's a ground state, it's an S state. And if you ionize it with UV light, such that it's a single photon process, you'll create mostly a P wave going away from that system. But if you ionize it with a two photon process, then you create mostly an S and a D wave, mostly D wave. Well, there's a different parity to a D wave and a P wave. That is, if you invert a P wave on itself about the origin, then you'll have an odd symmetry. It inverts itself, the angular distribution, the wave function changes sign. But for a D wave or an S wave, those are even wave functions, and they don't. So now if you can invert, the net result is that we get constructive interference in one direction and destructive interference in another direction. You can control the direction of electron emission in this system. So here's a simulation now where we just look at equal amplitude waves going away, and we change the relative phase of those different waves, again by controlling the optical phase. And you can see that in the first figure we have mostly ejection upwards, and by the time we change a phase by pi, we get ejection of the electrons downwards. How do you do that in the laboratory? Pulsed dye laser pumped by a harmonic of a YAG laser again. So it generates the light which we're using for the two photon ionization process. This is at around 580 nanometers, which is a nice yellow color. That's why I chose yellow for my arrows. We separate the beam into a couple parts. We have a harmonic crystal here which generates the second harmonic. So just like the third harmonic I talked about before, this takes 580 nanometer light coming in and converts it into 200 and whatever half of 500, 290. We recombine the beams. We again need to be able to shift the relative phase between those two beams. And so we do that in a delay cell here. And then inside of our vacuum chamber, we have a beam of rubidium atoms. And we positioned 4 detectors around it. This was all with horizontally polarized light, so we positioned 2 detectors which were in a horizontal plane, one which was perpendicular, and one which was at 45 between those two. And this is the signal that we detect on each of those 4 detectors as we change the relative phase between the 2 optical signals. So you see good strong modulation of the electron signal in channel 1. Channel 4, you see good strong modulation, and notice that this is perfectly out of phase with the modulation of this signal. So if the electrons are going to the left, they're not going to the right, and if they're going to the right, they're not going to the left. And then we see decreased modulation in the other directions as expected. And so that was the first demonstration then of control of the electron distributions. So other people were watching some of our work. I want to mention them as well. Shortly after that, Robert Gordon at Illinois at Chicago did work related to our mercury work. He was able to control the transition rate in a couple of molecular systems. He's a physical chemist, so he does his work in molecules. He also followed that then with a control of dissociation products. So one of the goals of this work, which really hasn't been met very well, has been, can you use this kind of coherent control in order to affect the branching ratio into different kinds of products? One success in that was this story. It's not quite to the point of calling it controlled chemistry just yet, but he was dissociating a small molecule HI, and he could control it by either ionizing it or by dissociating the molecule. And so he showed some control then on varying the phase that would change the relative amplitudes to those two different product states, and he could show some control out of that. Lou DeMauro, who was at the time at Brookhaven, did some work on HD plus and was dissociating that again. Some work that followed on from the atomic angular distribution work we did it was carried on in semiconductor materials, where you could control the direction of photocurrents in the semiconductor material. I believe this was done in gallium arsenide, but several notable works across there. Again, the idea of being able to control the outcome of experiment, nice proposal type demonstration by Nakajima showing you could control or take advantage of the phase differences. So we were continuing to work in the angular distribution work, and the earlier work I showed you had 4 discrete channels to it. We advanced then to make a continuous distribution. In that case, we're using now as our detectors microchannel plate detectors. These are glass-like structures. They're porous. They have a coating on them, which nobody knows what it is. But as the electrons hit it, they're going to rattle along the channels of this and get multiplied. So you get 1 electron in, gives you 1,000,000 electrons out. It hits a phosphor screen, and you can look down and see where those electrons were incident. So in this case, we're coming in, still rubidium, coming in with our omega 2 omega combination of light. Intersects the rubidium. We're doing this in a weak electric field so that the electrons, as they come out, get swept up towards the microchannel plate detector, and we can create an image then of the electrons as they are incident on that phosphor screen. And these are some of the images that we are able to collect for that. On the left side, I have just a P wave lying on its side. So you all remember from your freshman chemistry classes P waves. Just picture a peanut that's in the horizontal direction. And the electrons are coming out mostly this way and symmetrically out this way. And so they'll get swept up and they'll hit the screen. And that's what you see across here is the projection of those electrons onto that microchannel plate detector. This is the image we got with the D wave. Now, in this case, that laser was vertically polarized. And so a D wave, think of a peanut with a skirt on it. So there's this ring around the center. And so you see the electrons that were ejected upwards keep going upwards. The electrons which were rejected down go down, get turned around, they hit in pretty much the same spot. But then there's this ring around the waist which is going to expand up and give you this image across here. So this is a D wave line, vertically. When we put both colors in at the same time, then we get the interference, and you can see constructive interference on the right and destructive on the left, and then we change the phase by pi and we get constructive interference on the left and destructive on the right. We tried a little bit with molecules, so this was work with Ed Grant in our chemistry department. He's now at British Columbia, but his favorite molecule was NO, and that was similar work in which we're using a pulsed laser first to create an initial state for us, but then we did omega 2 omega type interference coming out of there and looked at the angular distribution, well, looked at the electrons coming off in this particular direction. And again, we could do modulation of the ionization signal in one direction as we change that phase. Now we did do a little bit trying to control ionization. This is still not chemistry, but in atomic barium, you can ionize the barium taking off an electron. You can leave the barium in its ground state. The electron carries off all the rest of the kinetic energy, and in that case I'm going to call those fast electrons because that's the barium's left in its lowest state and the electrons have all the rest of the energy. But barium also has, the barium ion has a fairly low-lying excited state as well. And so if we leave the barium ion that state, then the electron has less energy to carry off, and I'll call those the slow electrons. And so we did ionization of barium. We modulate the relative phase between those laser fields. We see modulation of the fast electrons and the slow electrons, and you do see a phase difference. This was, of course, the best case. You see a phase difference between the modulation of the fast and slow electrons, and that's one of the signatures you need for doing control over which product state you're creating, because if you have constructive interference leading to one product at the same phase as you have destructive interference for the other product, that's the best case for being able to control the outcome. Okay, so the idea of control then, at least in gases, can work. There are difficulties as you go to condensed phases because you're depending upon these two laser fields to have the same relative amplitude, the same relative phase as you're going through some condensed phase system. That becomes difficult, and after a while, some interest started to move in different directions. Our interest moved towards using this kind of an interference to make detections of very, very, very weak optical interactions. So I'm going to go back to analogies with optical signals. And again, well, in an optical signal, if you have a very weak signal you're trying to detect, here I'm picturing you have a source, you have a detector, the signal is weak, and you have some small current which is generated across there. If that signal is weak, that can easily be less than the shot noise, less than other sources of noise. It can be hard to detect. And so in the optical regime and in the radio frequency regime, people have developed homodyne and heterodyne detection techniques in order to dig optical signals out of the noise. And how that works is that you still have the same weak signal, same detector across here. You combine your signal with a much stronger local oscillator beam. And now what you detect here is the coherent sum of these two. So if these two signals are at the same or similar frequency, now what I will detect is going to be the sum of those two field amplitudes squared. That's my photocurrent would be proportional to that. If this is very strong, then I'll get this signal plus a cross term plus the weak field squared, but that's so weak that I didn't bother to write it down. If you can change the relative phase between these two, well, you have this DC term, which is just constant, and you have a term now which is at a beat frequency or a control. You can control the phase between them and make it constructive or destructive interference. So that's a signal detection technique that has been developed in the optical regime. That's going to be similar to what we're doing in our atomic system, except the same caution, we aren't doing optical interference. This is quantum interference between different transitions which are driven by the various laser fields. Okay, the direction we're heading in for this, and this is a current program now, is measuring very, very weak transitions which are induced by the weak interaction in the atomic system. Almost everything we need to understand about atomic systems, we can neglect the weak interaction. We have electric forces of the attraction or repulsion between the charged bodies. We have magnetic forces that show interaction between this spin and that spin or that orbital angular momentum. Almost everything is very nicely described in terms of electric and magnetic fields. One of those is that you can never induce a transition from an S state to an S state because that's going to violate parity. That's with an electric dipole transition, I should caution. So that's a forbidden transition by electric dipole selection rules. The weak force between different elementary particles, though, is different. It doesn't obey the same parity, and in fact what it will do is the S state is not purely an S state. It's going to, through this weak interaction with other states, it's going to mix in a little bit of a P wave. This S state will not be pure S state. It's going to mix in a little bit of P. Likewise here, it's going to mix in with a different parity state. So now you can imagine an electric dipole transition between this S state and the P part up here, or between this P part and that S state. It now allows a very, very weak transition, and if we can detect that transition, that can give us a way of doing high energy physics in an atomic laboratory. Why do we want to do that? Well, one motivation might be the search for dark matter. That's one of the pressing needs within the physics community these days. We know there's a lot more mass out there in the universe than we can account for. What is it? We have no idea. So theorists are able to hypothesize various scenarios that might explain what these are, and from those calculate what might be observable. Okay, here is a plot of a lot of data. This is years and years worth of data of what's known as the weak mixing angle, which comes from a measurement of the weak charge. These measurements are high energy electron-electron scattering. There are other proton scattering events. And way down in here at the lowest energy, this is plotted as a function of the collision energy between particles. At the lowest energy is the best available atomic parity violation measurement. In the different color bands across here, Marciano has plotted what he would expect for this weak mixing angle as a function of energy if there is a candidate for the dark boson, which is at 50 MeV in the green, at 100 MeV in the blue, or at 200 MeV in the red. These measurements are in progress, trying to improve their error bars. They're in the range where they could make a good yes or no decision about some of these models. But you can see down here in the lower energies range where atomic effects are greatest, that if we can reduce the error bars in the best current measurement, that we could make some inroads into this kind of discrimination. Okay, there are also some other effects which can be important, which are due to the weak force between the nucleons within the nucleus. And they can be found by looking at what are known as spin-dependent effects. If we can see a difference between different hyperfine components of the ground state. I won't go into a lot of detail there, but we are actively pursuing that as well. The best current measurement of the parity violating, again, does see a difference between these hyperfine transitions, and that's a much bigger difference than can be explained by any current models. That's been a standing problem since its first report in 1997. There are efforts in many other laboratories to measure parity non-conserving interactions, weak force interactions in atomic systems. The measurements which are complete, well, the best measurement is cesium. That came out of the laboratory in Boulder by Carl Lyman. He got the Nobel Prize, but for other work. Thallium, ytterbium, lead, and bismuth have all been completed. Ytterbium is notable because its amplitude for the effect is 100 times larger than in cesium. Yet still, they're at about an 8% level here. Active program in francium. Francium has the disadvantage that it's radioactive, so you have to do that at the accelerator laboratory where it's created, and you have, well, radioactive stuff's not so nice either. That's a collaborative program between Maryland, British Columbia, and Triumph. People are looking at various ions, and there's even some work in molecules for this. Anytime you're trying to measure something which is very, 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 very weak, you have to worry about things which aren't quite so weak and how you're going to discriminate the signal you're looking for from those other signals. So it's good to keep an eye on what else is available active on this transition. There is a Stark-induced transition. If you apply a DC electric field to your atoms, that's going to mix states as well, and that's going to allow at some level a measure of the signal which, well, one, it could interfere, but two, you can take advantage of it. We'll do both. There's a magnetic dipole transition. In units to keep track of these different levels, a strong transition in an atomic system typically has a magnitude of EA naught, where E is just the electric charge and A naught is the Bohr radius of the system. So that's a typical transition amplitude for an electric dipole transition. There is a magnetic dipole transition here, which is 6 orders of magnitude weaker than a typical strong electric dipole transition. We've actually measured that as a warm-up, and I'll show some data on that. There is an electric quadrupole transition here. It's weaker than a magnetic dipole. Fortunately, on this transition, it's forbidden, so it doesn't show up at all. And then our weak force-induced transition, which we're looking for, has an amplitude of about 10 to minus 11 on this same scale. So it's a challenge. I'm not going to say it's an easy measurement to make. All these measurements do depend upon having good theory, because after you measure what the amplitude is, how do you convert that into the charge of the weak force? And so we depend upon having good theory to do that. That's one of the strengths of cesium, actually. Cesium is rather hydrogen-like in its structure. It's an alkali metal, so it has this nice symmetric S-wave function as the initial state. And the efforts of theory are, the theorists are critical. There is some discrepancy in the two best theories right now. That needs to be resolved, and Mariana Safronova at Delaware is, or will soon work on that. We often get asked the question, well, cesium has been done and it's the best current value, so why go back and do cesium? Why don't you go do something which is new? And we have some good answers for that question. One is that we do depend on very, very good theoretical modeling of the atomic system. And cesium, not as good as hydrogen, maybe not as good as helium, so maybe it's in third place now in the best studied atomic system in which you can actually depend upon the theoretical models in order to understand the magnitude of this effect. There are also very nice experimental techniques that we can apply in any of the alkali metals that are not available in other atomic systems. One of them is optical pumping. We can use lasers in order to shift the complicated ground state structure into a single initial state. Detection efficiency. If you're just going to put a detector beside it and look at fluorescence coming off, your detection efficiency is going to hurt. Maybe less than 1% detection efficiency just due to the availability of good detectors and the solid angle of detection across there. We're going to use an efficient detection system based upon optical cycling of the transition. And also, in the measurements that we're describing here, we're doing all continuous wave measurements, and so we get nice accumulation of data over long runs. In the first part of what I talked about today, from our initial measurements through the barium work that I talked about, those were all done with with pulsed lasers, which 10 nanosecond duration pulses, and they eject electrons in that time. This is all done now with stabilized CW lasers and detectable signals with that, but continuous. Okay, I think I'll skip these. I do want to emphasize the stability, though, because we're competing with the francium measurement. Okay, so a measurement that we have completed is a two-photon transition on the same transition we're talking about for the weak interaction. It's from the ground state, success state, to the excited state. We're using this transition at 852 nanometers for measuring the signal, and we're just trying to see, well, how much have we transposed? How much have we transitioned? So again, the transition amplitude that I'm looking at is the sum of all the amplitudes that are possible. We have the two-photon process, which was never used before, and that's driven by a laser in the infrared at 1079 nanometers. We do have the magnetic dipole, that's what we're trying to measure. And the Stark-induced transition, that's going to be our standard, our reference for these measurements. The total transition rate depends upon the square of those, just like with the optical homodyne detection I showed. We have that term squared, which is huge, and then the cross term between these two guys and the two-photon rate, which is small, but we can control it. We can change the relative phase between these two guys and this one, and from that relative phase, make them interfere constructively or destructively, see an enhancement or a diminution of the signal, and from that, know the amplitude of the cross term. The cross term gives us the magnitude that we're looking for. And I put this up here just because we are combining the magnetic dipole transition with a Stark-induced transition. It's actually the quadrature sum of those, which is important. That actually is to our advantage as well. So here's some data on that magnetic dipole transition. We are driving the transition from the 6s to the 7s. We have the strong two-photon transition. We have the weaker magnetic dipole and Stark-induced transition, and we change the phase. And here I've plotted against the phase across this axis. You can see very nicely the modulation of the signal. This is the interference. This is on top of, this is just the modulating part. This is on top of a DC part, which is about 10 to the fourth times larger. The key, though, is here we do it with a zero electric field applied to it, no Stark effect, so that's just the interference between the magnetic dipole transition and the two-photon transition. Then we turn on the electric field. Now we have, in addition, the Stark-induced transition. You can see a stronger modulation amplitude. Okay, so it's a different scale by a factor of 2, plus the amplitude appears a little bit bigger. That's the primary measurement for this. When we plot the amplitude of that process versus the strength of the DC field, we get this hyperbolic function. We can fit that and determine from that the ratio of the magnetic dipole amplitude to the Stark-induced transition. That's our calibration standard. We can also get the sign of that. I'm going to skip that, but the sign of the magnetic dipole transition is important. We repeat the measurement lots of times under different conditions, different initial states, different hyperfine transitions, and the average value now of about a 0.4% accuracy to the measurement. That is in agreement with other measurements that have been carried out. Theory isn't so good on this transition. They're off by about, I think it's about 15% or so. So theorists have some work to do on this one. Okay, so that was the magnetic dipole transition, and that's 6 orders of magnitude weaker than a typical electric dipole transition. And now we're hoping to apply that same technique to measure the weak force in the atomic system. That's 5 more orders of magnitude, well, greater than 4. I don't want to be too pessimistic. Weaker. How do you do that? Well, first we have to change the orientation of fields. That's a rather trivial thing, but we use the polarization of the laser, we use the direction of the applied electric and magnetic fields to our advantage in order to pick out the transitions that we want. That's a good start, but that's not going to be enough. We're going to use an optical build-up cavity. So we're going to put our light that drives the transition into a resonant cavity. We can get a finesse of 10,000 or so. We can enhance the amplitude of the field which drives that transition. We're going to use counter-propagating laser fields. That's going to affect that the magnetic dipole amplitude that we just measured will cancel itself. The beam going through in one direction, these are selection rules which are important to us but maybe not important to you. Different directions we can deplete that or diminish that magnetic dipole contribution. And the critical part here will be to really control the static electric fields. This is to the point where oftentimes as you have structures within a vacuum system, nice polished copper surface or something, over time it's going to build up vacuum oil, it's going to build up cesium atoms which are floating around, and they develop what are known as patch effects due to domains within the copper structure. Those effects can affect these kinds of measurements because the electric field generated by those effects can be larger than the DC electric field that you apply. So those are things that we have to deal with. We do have a parallel effort. I made the point that we're trying to measure hyperfine effects and the effect of the nuclear effects going on. So a parallel measurement now is to carry out a similar measurement on a transition between the 2 ground state atoms of the cesium. This is the 9.2 gigahertz signal that atomic clocks are based upon. So your global positioning system, your cell phones, your Google Maps don't work unless you have these good atomic clocks. This is one of the transitions used for that. We'll drive the transition again with the interferences. In this case, the 2-photon transition is going to be by a Raman type process, coupling the 2 hyperfine levels. And we have now our magnetic dipole and our parity non-conserving interaction and our Stark-induced interaction on that system. There are similarities between this measurement and the measurement I've already described. There are also some pretty fundamental differences as well, but the key here is that this measurement is going to be due only to the nuclear spin dependent terms. And so it's a better measurement now for picking out the what's known as the antipole moment of the nucleus. We have some experimental tricks that we're going to play with, and I think I'll spare you many of those, but we are, again, borrowing from many of the same things that we did in the other system, and we've done some modeling of these laser fields. We are developing a parallel plate structure for transmitting the RF waves that drive this, and being able to apply a DC electric field that's perpendicular to the RF polarization. That becomes rather tricky, but we think we have a good scheme that can do that, and we're fabricating the boards now. And we've done some modeling of the laser field, the modes of the cavity. We're creating an RF cavity that we can use to control the RF field. This is for the 9.2 gigahertz field. We'll work at the antinode of the electric field, which is the node of the magnetic field, and hopefully reduce the magnetic field effects due to that. So, over the years, we've been able to use the interference first for just controlling the transition amplitude. We can turn it on, turn it off is probably too strong a word, but we can modulate the probability for the interference to take place. We've used it for controlling the direction in which the electrons are ejected. So we can make them go right, or we can make them, for your way, left or right, just by controlling the relative phase between the laser fields that are driving the transition. We've done a little bit of control on the population of various channels, not to the point where you could call that chemistry, but that's one of the goals of the work. Our more recent work, though, has been to, instead of using it to control the products of the outcome, we're using it to detect a very weak amplitude as contrasted with a stronger transition. So we're looking at a very small change in amplitude as we change the phase of the relative field. So thanks for your attention, and thanks for coming today.
Thanks very much. Any questions? It could be technical or career.
You've all been very well behaved. Yeah, Vlad.
I just it happened so I was just in the European Research Council panel, and they put lots of money into a project actually to observe this Coherent and conserving optical manifestation. In that particular effort, they tried to look at polarization effects because we know they have very strong sensitivity. So basically chirality effects, but normally left-handed and right-handed
yes.
completely balance each other.
Right.
But because of PNC, there should be some rotation. So that is a big multi-million-dollar effort now. Exactly.
I've seen some of that work. There's also been some work at trying to...
It's polarization. We know that it's exceptionally sensitive when they measure polarization.
Yeah.
And the chirality, that's specifically what they're looking after.
Okay, that's interesting. Thank you. Andy.
So, you talked a lot about playing with laser phase, observing the effects of the interference. Transitions themselves presumably can have some phase that they add.
What can have?
The transitions themselves, the quantum mechanics. You know, particularly as if you were to tune the laser.
Yeah.
Some resonance. Do you ever, use this to make measurements of or worry about what the phase added
so,
by the actual by the matter in the quantum mechanics?
So bound states will always have a real quantity. So it can change the sign, but there won't be a continuous phase there. Scattering states, as we access when we do ionization, will in fact have a phase to that continuum channel, and yes, we've measured that. We have some improvements that we think we could make if properly motivated, but we have done that kind of a measurement in the rubidium work.
Any others?
I'll go one more. So this last one, trying to measure these extremely weak transitions.
Yes.
What do you characterize as the time scale for being able to build up, hopefully build up the sensitivity and the control to make that measurement? In years or in terms of PhD students, however you want to.
I notice that George is watching attentively to what my answer is going to be.
I can speak quietly.
There are a lot of systematics that need to be dealt with. You have to really understand the stray fields within the system. You have to understand how you're controlling things. George is working diligently on decreasing the bandwidth of the laser so that it's very well controlled as well and stabilized. I'm going to say that we will have the work completed before I retire. And in terms of number of students, a few. Is that fair? George? You good with that one? Okay.
If I may also make a comment, because thinking of possible applications of all this fascinating stuff you did. So one thing you mentioned that to control chemical reactions
yes.
by controlling phase, that's relatively old already activity, even though it did employ it. So, but there are a few the newer things which people actually now very much after, like hot electron production, photocatalysis, hydrogen production, water sleeping, and those also should be very sensitive to phase if you have more than one optical channel of excitation. And take into account that all it's related to energy production, storage, conversion. I think that could be very interesting. To my knowledge, nobody looked at the phase interference effects.
Not that I'm aware of.
Very, very important processes.
Okay, thank you.